Hello everyone, let's talk about another medium problem on Leetcode today. Number of good leaf nodes pairs, Leetcode 1530. In this problem, we are given a root of a binary tree and an integer distance. Then they have defined what is good leaf node pair. A pair of two different leaf nodes of a binary tree is said to be good if the length of the shortest path between them is less than or equal to distance. Return the number of good leaf node pairs in the tree. So then they have given some examples as well. In example 1, the distance given is 3 and the tree is given like this. The number of good leaf node pairs is 1 because there are only 2 leaves, that is 4 and 3, and the distance between them is 1, 2 and 3. This is less than or equal to the given distance, and that's why we return 1 in this case. Then in example 2, the distance is again 3 and tree is given like this. There are 4 leaves present in the graph, 4, 5, 6, 7. Then there are two good pairs, that is 4, 5 and 6, 7, because the distance between 4 and 5 is 2 here, right? Then similarly, the distance between 6 and 7 is again 2, which is less than or equal to given distance 3. So they are good pairs. But the pair 4 and 6 are not good pairs because distance between them is 4, which is more than given distance 3. And we go from 4 to 2, then 2 to 1, then 1 to 3, and then 3 to 6, right? So that is why the distance is 4 now. So that's why we just return 2 in this case because there are only two good pairs. Now let's see how we can actually solve this problem. So initially when I was trying to solve this problem, I was thinking to actually find out all the leaf nodes initially. So that will take like O of n time, right? For example, now we found out leaf nodes 4, 5, 6, and 7. So the idea is simple, that go do the DFS on the tree and see if the left and right child are null. If yes, then that means this is a leaf node and we add it to the list of leaves for now and then return. And then for each leaf node pair, we try to find their LCA, that is the lowest common ancestor, because shortest path will always go through it. So for example, the shortest path between 4 and 5 will be this. Similarly, the shortest path between say 4 and 6 will actually go through this, as 1 is the LCA. So to find the shortest distance for each leaf node pair, we will actually start finding their lowest common ancestor and calculate the distance of these leaves from the lowest common ancestor, add them up, and get our shortest distance between the two leaf nodes. For example, for 2 and 4, it will be 1 from the lowest common ancestor, and 2 and 5 will also be 1. So overall, the shortest distance will be 2. Similarly, for say 4 and 6, the shortest distance will be 2 from here, and 2 between 1 and 6, right? So this, the shortest distance will be 4. So this is how we will calculate the shortest distance between two leaf nodes in the tree. And then whenever we are calculating the shortest distance, we check whether it is below the threshold. If it is, we will increment the answer. Otherwise, we will keep the answer as same. So finding the shortest distance between two leaf nodes takes O of n time, right? Because we have to find the lowest common ancestor between two leaves, that takes O of n time. And then finding the shortest distance between the two leaves again takes O of n time. So overall, the time complexity for finding the shortest distance between two leaves takes O of n time. And suppose the number of leaves are d. That means to find the shortest distance between the two leaves, we are running this loop d square time. That means we are finding the shortest path O of d square time. So overall, the time complexity will be O of n d square. But then I realized that the code for this will be a lot more and the complexity will be higher as well. And the question is, can we do better? And answer is yes. So instead of actually calculating the LCA manually, how about we actually do the DFS or do the post order traversal? So whenever we find the leaf node, we actually start calculating the distance of the nodes from the leaf. So for example, suppose we found leaf node 4. Now because it's a post or a traversal, we will go to the parent, that is node 2. Now the distance will be equal to 1. Similarly, when we found out the leaf node 5, because it's a post or a traversal, we will find the leaves first. Then we again go to node 2, and now the distance of node 2 from node 5 will be again 1. So then 2 actually lies on the shortest path between 4 and 5. So in a way, it's like an lowest common ancestor. And in this case, shortest distance is 1 plus 1, which is 2. And it is less than the given threshold distance. So it is a good leaf pair. So similarly, the distance of 3 from 6 and 7 will be 1, right? And again, the shortest distance will be 2. It is less than the threshold distance of 3. So 6 and 7 are also a good leaf pair. So we have two good leaf pairs so far. Calculating the distance from one pair of leaf node was easy. But now how will we actually apply the same logic on the parent node? That is 1. So in this case, if we look carefully, we don't have to return the distance between 4 and 5 anymore, but we have to still calculate the distance between 4 and 6 or 4 and 7, because the shortest path between the leaf nodes 4 and 5 will not contain 1 in it, right? So we only care about the leaves where 1 is LCA. So for example, for leaves 4 and 6, 4 and 7, 5 and 6, 5 and 7. So in this case, instead of returning one distance, we will be actually now returning a list of distance. So, and because we have to compare the leaf pairs, instead of returning a distance, we will actually return the list of distances. So we will return the list of leaf distances on the left side and list of leaf distances on the right side. So we calculate the list of leaf distances of leaves 4 and 5 and 6 and 7 from node 1. So this is again simple, because now we are at node 2, we go up. So now we will increment the distance of leaf 4 and 5 by 1. So now they both become 2 and 2, right? So those are the two distances. Now we will get the list of distances from the right side as well, right? So whatever are the leaf nodes on the right side, that is 6 and 7, we will again increment their distance by 1 to go to the parent node 1. Again, the distance is 2 for 6 and then 2 for node 7 as well. Now we sum up the distance between the leaf nodes on the left side and the right side. So for example, the distance between node 4 and 6 will be 2 plus 2, which is 4, and it is greater than threshold distance. Similarly, the distance between 5 and 6 is also 4, which is again greater than given threshold distance 3. So all the pairwise leaf distances will sum up to 4, which is more than threshold, and that's why we will just return 2 in this answer. So our idea is simple. We will just do the post order traversal. On each path, we will actually track this answer variable, where whenever we see a good pair, we will actually increment it by 1. And for each node, we will actually return the list of distances of this node from the leaf node, right? And that's it. And we don't have to calculate any LCA or anything. It's actually automatically taken care of by this post order traversal. So now let's, I hope this was clear to you. Now let's jump into the code part. So we will need the answer variable, and I'm using the array here because Java is passed by value. So to overcome this, we can either use the object reference like this array object here, or we can define the attribute inside the solution class. So each time we actually see a good leaf pair, we will actually increment our answer by 1. Now we start the TFS. So we will pass a root, distance, and answer to it and return our answer variable. And now comes the interesting part. So we will just need TFS function. We pass in node, the distance, and the answer. And we are returning the collected leaf distances from the current node. So whenever we see node is equal to null, we will return empty array because it does not have any leaf node at some distance from it. Similarly, if node is a leaf node, that is node dot left is equal to null and node dot right is equal to null, we will return one leaf distance equal to 1. Now we will do the DFS. We will get all the leaf distances on the left side. Similarly, we will get all the leaf distances on the right side. And now we will do the post order processing. Now we will pairwise add the left and right distances. So we will loop on the left distances and the right distances and see if the sum of the left distance and the right distance LD plus RD is actually less than equal to threshold distance. Then we will actually increment our answer by 1. So now we have our answer for this node, but now we have to combine these distances for its parent. It will be at maximum of length, the left distances and the right distances. Now we will be looping on this distances array using index variable and do a small optimization. So we will propagate only those left distances where the distance value is less than distance minus 1. I will explain why. So if LD plus 1 is less than distance, then only make it part of the distances array. So that is the maximum number of distances possible, but we don't have to pass on all the distances. So note that I'm doing left distance plus 1 because I'm incrementing the distance now when we are going to the parent. So that is one thing. But also I'm checking this distance should be less than the distance, right? Because if it's equal to distance, or let's call it threshold distance, then the parent will also get something from the right child, right? So at least that value will be 1, and this value will again be more than the threshold. distance. So instead of that, we send the maximum distance equal to threshold distance -1, so that parent has a room to actually incorporate the right child as well, because we need two nodes to calculate the distance, right? So this is one thing. Similarly, we will do the same thing on the right side. We have to also at max pass the distance -1, so that we can incorporate the distance from the left side. And once we are done, we will just return part of this distances array up to index variable, right? So we will just do arrays dot copy of distances array up to the length of index. So once this is done, let's run this code. There is some issue. I should pass new int, right? My bad. I should initialize the array. Now I think let's try it out again. For some reason, I have index out of bounds. Let's see what is the issue. Because I am looping on the wrong array. I should be looping on the right distances array. Sorry for this typo. Awesome. Now let's submit this code. Cool. In terms of time complexity, it is again O of n into d square. We couldn't do better there, but at least the code is cleaner. N is the number of nodes in it, and d is number of leaf nodes in it. And the reason for this is we are doing the DFS, which takes O of n time. And then we are running this loop, which is running on the leaf nodes on the left and right side. So that takes O of d square time. So that's why the overall time complexity is O of n d square. And in terms of space complexity, it is O of n, because if you think about it, we are using recursion stack for DFS. So that takes O of height, which is in the worst case equal to O of n. And we are using these left distances and right distances. And in the worst case, again, they can be equal to n. So they are actually proportional to n. So that's why I'm saying the space complexity is also O of n. I hope this solution was clear to you. If it was, please like and subscribe. Have a nice time. Thank you.